All right, let's dive in. Today, we're talking about the internet's unsung hero, the transport layer. You can think of it as this incredibly smart postal service that manages every single piece of data you send and receive. It's the real reason some things you do online are just flawless, and while others not so much.
You've probably wondered about this, right? It's a great question because it cuts right to the chase of what the transport layer is all about. For every single thing you do online, it has to make a choice. Do you need it fast or do you need it perfect? And the answer to that question explains everything.
So here's what we've got on tap. We're going to look at the internet's big delivery problem, meet the two main messengers, that's TCP and UDP, and then see how they handle things like speed differences and network traffic jams. And to wrap it all up, we'll see this efficiency stuff in action. So what's the big challenge here? Well, we need to send just mountains of data across this sprawling global network that is, by its very nature, totally unreliable. Seriously. Packets get lost, they get corrupted, they show up in the wrong order. It's a mess. And the transport layer is what steps in to clean it all up.
And this is its job description. The transport layer doesn't just shuffle data from one computer to another. No, it's much smarter than that. It moves data from a specific application on your computer, say your web browser, to a specific application on another computer, like a web server. It does this using something called a socket address, which is just a combo of an IP address and a port number. It's like a super specific mailing address that makes sure your web traffic goes only to the web server, not to your email app by mistake.
Okay, so to handle all these different kinds of jobs, the transport layer has two main delivery services. Two messengers, you could say, and they have very different ideas about how to get the job done. Let's meet them. On one side, you've got TCP, the Transmission Control Protocol. This is your certified courier, right? It tracks the package, it gets a signature, it makes absolutely sure every single piece arrives safe, sound, and in the right order. Then you've got UDP, the User Datagram Protocol. This is your postcard. You just scribble a message, drop it in the mail, and hope it gets there. It's ridiculously fast, but, no guarantees. Now this is where it gets really interesting. Just look at the header size. TCP's header is anywhere from 20 to 60 bytes, while UDP's is this tiny, fixed 8 bytes. So why the huge difference? Well, that bigger TCP header is basically the price you pay for reliability. It's filled with all the paperwork needed to be that certified courier, sequence numbers, acknowledgments, all that good stuff. UDP just throws all that out for pure, unadulterated speed. And this slide shows you exactly when you'd use each one. For things where every single bit is critical, loading a web page, downloading a file, sending an email, you absolutely need the reliability of TCP. But for things where speed is king, like in a fast-paced online game, a video stream, or a voice call, you go with UDP. I mean, think about it. A slightly pixelated video frame for a millisecond is way better than the entire stream grinding to a halt, right? And just like that, we've answered our first question. Okay, so we've picked our messenger. But no matter who you choose, you run into this fundamental problem. What happens when the sender is way, way faster than the receiver? This brings us to a really important idea called flow control. The key thing to get here is that flow control is a direct one-on-one conversation. It's all about making sure the sender doesn't just flood the receiver's inbox, It's basically the receiver telling the sender, hey, slow down. You're talking way too fast for me to keep up. Now, the most basic way to do this is with a protocol called stop and wait, and it is exactly what it sounds like. The sender sends one tiny packet, and then it just stops. It does absolutely nothing until it gets an "okay, I got it" message, an ACK, back from the receiver. It's super simple, totally safe, but as you can probably guess, it's incredibly inefficient. This formula really drives home the problem. The letter A here is basically just a ratio of how long you have to wait for the ACK to arrive versus how long it took to send the packet in the first place. On a long-distance connection, like across an ocean, that travel time is huge. And because you have to wait for a full round trip, there and back, that 2A term gets really big, really fast, and your efficiency just tanks. It basically proves that most of the time, your connection is just sitting there, twiddling its thumbs. So, obviously, stopping and waiting all the time just wasn't going to work. We needed a much smarter way to do things that didn't involve so much, stopping and waiting. And that smarter approach is called the sliding window protocol. This table is a perfect roadmap of how things got better. Instead of sending just one packet, we create a window of, say, N packets that can all be sent without waiting for an ACK. Go back N is a big step up, but it has a flaw.
If packet number 3 gets lost, it makes the sender go all the way back and resend everything from packet 3 onward, even if 4, 5, and 6 got there just fine. Then you have selective repeat, which is the smartest of the bunch. It lets the receiver say, hey, everything arrived except for number 3. Can you send just that one again? It's way more efficient, but it does require a bit more brain power on the receiver's end. Okay, great. So flow control solves the speed mismatch between one sender and one receiver. But what happens when thousands of devices are all screaming to send data at the same time, creating a massive traffic jam on the internet highway itself? This is a much bigger problem, and it calls for congestion control. And this is the absolute key distinction. Flow control is about protecting the receiver from getting overwhelmed. Congestion control is about protecting the entire network. It's a community problem, trying to make sure the routers and cables in the middle don't just melt down and start dropping everybody's data. TCP has this brilliant adaptive strategy for this. It kicks off in slow start, where it basically floors it, exponentially increasing its sending rate to quickly find out how much room there is on the road. Once it hits a certain point, it switches to congestion avoidance, where it eases up and grows slowly, just kind of tapping the gas to see if there's any more space. But if it detects a traffic jam, which usually means a lost packet, it hits congestion detection, slams on the brakes by slashing its sending rate, and then very carefully starts the process all over again. All right, enough with the theory. Let's put some real numbers to these ideas and see how it all plays out in a practical example. Okay, here's a classic problem that ties this all together. We're using the go-back-end protocol. We know how long it takes to send a packet, we know the travel time, and we know our window size is 10. The big question is, how efficiently are we actually using this connection? Let's walk through it. First, we calculate that A value, which is just travel time divided by send time. So 40 divided by 20, that's 2. Simple enough. The formula for efficiency is the window size, n, divided by 1 plus 2a. So we plug in our numbers. That's 10 divided by 1 plus 2 times 2. So 10 divided by 5, which gives us 2. Huh. Wait a second. 2? 200% efficient? That can't be right. You can't get more out of a connection than its total capacity. How is that even possible? And you're absolutely right. You can't. A result of 2 doesn't mean it's 200% efficient. What it really means is that the link is running at 100% efficiency. Think of the connection as a pipe. To keep that pipe completely full of data at all times, you need to send a certain number of packets. In our case, that magic number is actually 5, but we're sending a window of 10. We're sending more than enough data to keep that pipe totally jam-packed around the clock. The link is never idle. We're at maximum capacity. And that really is the perfect way to sum it all up. The transport layer is a masterclass in making the right trade-offs. It's this constant, dynamic balancing act between going fast and being perfect. So the next time your game stutters for just a split second, or that huge file you downloaded arrives without a single error, you'll know why. It's the transport layer, deep in the machine, choosing the right messenger for the job, making sure the internet just works.